Hi there everybody, this is Hammond from Sandia Labs, and I'm here today to talk to you about some of our early experiences with the A64FX processor from Fujitsu. We're really excited to come talk to you today about some of the work we've been doing on these processors, and all, we wish it was in person so we could see all you guys. We know most of you, or know many of you, so hopefully that won't be too far from now at another SC. The work today I'm showing is just mine. It's from a team of people here at the labs, and I'm super happy to be able to acknowledge some of those guys here and some of the other team members later on in the presentation. So let's get started. Just an overview really for what we'll talk about. We've got some initial A64FX test beds in house. We'll talk about those. We've got some extra hardware on the way, which we're going to put into some different networks and some different systems. So what you're seeing today is really our initial take on that, initial hardware that we've brought in. We'll talk about some of the performance results that we're seeing on those systems, different compiler combinations, and how that sort of compares to our contemporary systems. We'll go on to talk a little bit about the ATSE software environment. So ATSE is our vision for a future programming environment where we really curate a lot of the packages that we put together in there, and we debug those and we optimize those so they give really good performance in an HPC environment. We'll talk a little bit about where we're at with porting that to the A64FX. We've got some good results to show there, and that will also touch a little bit on COCUS, our COCUS C++ programming model, and our TRILAB solver stack when we get to that point. And then I'll just give you some pointers and stuff for some other resources at SC'20 the members of the team here are going to be talking about. So let's start really and talk about the A64FX testbeds at Sandia. So A64FX outside of Fugaku is relatively new, so we're really lucky to be able to get our hands on some of those. For those of you who have followed Sandia's talks at SC and different conferences over the last few years, you'll know that we frequently make reference to this project we call the ASC Advanced Architectures Testbeds, and that we've really been working on that for nearly a decade now, a long time. The purpose of that project is really to bring novel systems, different processors, different GPUs, different accelerators, and different interconnects into the lab, and then they could be at prototype stages, they could be products, but typically they're sort of pre-product stages when we get them, and that enables us to test in NSA mini apps and benchmarks and some of our workloads, our important kernels on that hardware, and to see if we can utilize some of the the novel features that these different chips, these different processors provide. So for something like A64FX, how efficiently we can use the high bandwidth memory and the SVE wide vector units on the processor, and see whether we can get gains out of those units for our workloads. The whole point of this really is ultimately to enable us to think about what features we'd like to see in future system designs and which ones of those are the most important for us. And it gives us a leg up on trying to port our software packages and really some of our codes onto this system early. So what do we get? What's the value return, and how difficult is it to use some of these systems? We've worked on ARM really, I think probably for about 7 years. About 7 years ago we were working on 32-bit ARM processors, doing the first work there and characterizing them. And of course we've got a long history there in working through processor designs from what was an HP Moonshot at the time through to Cavium, the first Thunder systems, the Thunder processors, to Thunder X2, which we deployed in Astra, and then on to A64FX. And most of the machines that we deploy in the test beds follow this theme of an American first. So these are pioneering figures from American society, really American history. And we're super proud to be able to show the A64FX test bed at Sandia. We call the system Inouye. It's named after Senator Inouye, who was one of the first Japanese American citizens to really achieve election and representation in the House of Representatives, and he went on to serve in the Senate. So we're really proud to acknowledge his service to the country and to name the system after him. The system, in a way, is relatively small right now, but we'll be adding resources to it. I said it was pretty early hardware. It's 8 nodes of A64FX connected with InfiniBand. It doesn't have the tofu network that you see in Fugaku, so just InfiniBand, but enables us to look at scaling on the node, to do node-to-node performance comparisons, and to get some idea of what network scaling would look like. Our particular system is integrated by Penguin Computing, but and they've been great. We've worked really hard with those guys on getting the nodes in. They've been very supportive, and I think you can get you guys can go get nodes from Penguin, and I think there's some nodes available from HP as well. But those particular results come from the Penguin nodes. So the first question everybody asks about A64FX is, what can you get out of this high bandwidth memory? Can you really get the numbers, really high levels of efficiency out of the processor? So I'll start by saying that, occasionally we can kind of tweak the benchmarks and the settings to get as high as 850 gigabytes a second. The HBM on that node can get about 900 to nearly a terabyte a second. So this is a very efficient memory subsystem. But the curves you're seeing here are kind of the results of lots of runs, and I think are representative of what we perhaps typically see. We've compiled them with different compilers. We've got the Fujitsu compiler there at the top in red, delivering nearly 800 gigabytes a second when we just run the benchmarks over and over again. So very substantial memory bandwidth from that compiler. The yellow here in the middle is what happens when we use GCC 10.1. We've noticed some fairly significant increases in performance with GCC starting from the 10 series on for this platform. We've been trialing different versions of GCC on there just to see what we really get out of them, but from 10 onwards you definitely see a big improvement. Down here in the blue at the bottom is sort of a contemporary node of ours. So this is a high performance Skylake Xeon Platinum processor. Nearly about 200 gigabytes a second from that, so very substantial. The Intel systems have typically got a lot larger capacity, like half terabyte, 256 gigabyte capacity, so we can put some really large problems in those. The A64FX has only got 32 gigs, so a lot smaller but a lot faster. So that sets up some interesting decisions for us for our code as we move forward. Some of our codes really need some larger capacity, and some really benefit from much higher performance. So this is really just a pretty good representation of what we're seeing on the nodes for memory bandwidth right now with the Fujitsu compiler. Lots of flags there that kind of tweak the memory bandwidth, but we can get some really good memory bandwidth increases there over, say, a normal computing node down around 200. So this is very promising. We've been very happy with the performance from the memory subsystem. That translates really into our linear solver packages. So this is the HPCG is a good example of this, but we've got Mini-FE as perhaps a simpler version of HPCG, but there's other packages like AMG or Hyper from Livermore, and then you'll find this in PETSI and Trilinus and everything else. So these are the things that underpin a huge part of the workload of Sandia, and so we're intensely interested in what the performance of these systems can look like when we're running linear solvers. Our experience has shown that higher bandwidth memory subsystems usually give us much greater improvement for linear solver packages, and that's exactly what we're seeing here. So this graph shows you, on the far right there with the Intel Skylake is in sort of dark blue. We're seeing 30 gigaflops, something like that, which is still a very substantial increase over performance that we've had from in the past. And you see the A64FX, which is really the three results on the left using different compilers. So the Fujitsu compiler again gives you the best performance here. It really does know how to optimize code on this platform for memory bandwidth. The ARM compiler there in the middle is the lowest of the three on this particular benchmark on the platform, but you'll see some differences as we move forward for some different codes. And then we've upgraded to GCC 10.2 here. It's still giving us pretty good performance in the yellow. So overall, about 2.18x increase over Skylake, so fairly substantial for Mini-FE. This is perhaps the simpler version of HPCG. So you see for HPCG, we're seeing around 1.6x improvement. So this is pretty substantial increases in performance, but you do need to get the compiler flags right for these. Fujitsu compiler has got a lot of flags there, and that can really significantly change the way that the graph turns out. So you've got to make sure when you get these right, it really knows how to optimize for streaming stuff from the memory subsystem, making the best performance there. So we'll go on to look at something like LULESH. This is HYDRODYNAMICS, unstructured. So most of our codes that I worry about at the lab, at least, are unstructured in their formation. So that means you don't necessarily know where the operands you're going to go and get are. And so you typically find that compilers generate lots of gathers and scatters around this code. It looks a lot more like a randomized access, and you don't get this streaming behavior from memory in the same way that you saw in the previous benchmarks. And particularly for something like LULESH, but also for other benchmarks that are in this sort of category, you see a much more aggressive use of something like a level 2 cache or level 3 cache on the processor. And if you look at the results at the top here, you'll see that the Fujitsu compiler here doesn't produce the best results. You see that the GCC is actually producing the best results here. So actually some really quite significant gains in figure of merit here. So higher is better. But we also see that the ARM compiler is also doing very well here on the particular benchmark. You see the performance sort of go up as the problem size increases a little bit, and then it starts to go down again as you move towards the right, and that's as you start to break out from the cache. So as the problem size gets bigger and you start leaving, more of the operands have to come from memory and fewer of them are available in the cache, you see the performance begin to drop. So that's why the performance is lower on the right with the larger problem sizes. And what we do is usually tweak this when we're running for real in production environments so that we get the best performance for the meshes that we're trying to use for our simulation. But this shows you down here on the bottom is, say, an A64FX versus Skylake, and you'll see here that Skylake is substantially higher performance, and that's because it's got very large level 2 caches, level 3 cache on these chips. So this is a Platinum Xeon, so these are the expensive versions of those processors with lots of cache. And then we're using the Intel compiler there. So if we compare the best performance we get on the A64FX versus the best performance we get from Intel, so this is using the best combination of compiler and run flags. You can see here that the Skylake is perhaps 2 to 2.5 times faster at this particular benchmark than an A64FX. And this is something that we do see. So when we're very strongly memory bandwidth bound, the A64FX does absolutely fantastic, and for a lot of our workloads that's really going to make a difference. When we're doing these more gather scatter heavy loops where latency is perhaps a little bit more important and you really need some large caches, that's where something like a Skylake can really come into its own. So there isn't one piece of hardware here that completely crushes everything. There's different optimization points in the hardware, and that justifies how we think about designing systems, that sometimes we're going to want one kind of hardware architecture and sometimes we're going to want the other. There's some work to be done here as well. We're pretty confident that the LULESH version that we have doesn't completely vectorize and take account for all of the capabilities of SVE. So we're continuing to work on this, and we've already actually got some better results from some of these optimized benchmarks where we've gone in and really looked at the code the compiler is generating, and we're still working to improve them. So expect to see some better results here on the A64FX over time as well. So let me just talk a little bit about where we're at with software really on the platform. So you got this new processor, we got to get SVE built into the packages, and we got to do lots of work to test and debug that. Our vision for that environment is really this product that we call ATSE, the Advanced TRILAB Software Environment. We've worked really hard to optimize that on Astra and for Thunder X2. We work with the folks on the ARM HPC compiler team and Math Libraries team to get the right level of optimization and tuning here, and it works with the ARM compiler and GCC. And we're adding, we've got that basically now ported over to the A64FX and building with native SVE support from GCC and from ARM. And we're working on that with the Fujitsu compiler right now. So still some work to go here, but the initial results are good. When you log into ATSE when you log into Inouye as a user today, you'll see an ATSE which is compiled to sit there and really use the platform with SV turned on as a compile option for most of these packages. So this is great. Underpinning this is the TRILAB operating system normally, and we're working with the folks at Lawrence Livermore to make sure that we can get this stood up on specifically on A64FX. That's got to be a Red Hat 8 compile today, because that's the minimum level of operating system you can use to move forward on A64FX. So the latest releases here are available. You can see there's some recipes at the link there, but there'll be an update for that as well with A64FX extensions over time, and we're working really hard to make sure that this is actually available for all our users who are logging into the system. And in the works, we've got Cocos and Trilinus both working on these platforms. I know we've got users out there that use both of these. So Cocos is our sort of vision for an abstract, hardware abstract or hardware agnostic C++ programming environment that can run across GPUs and CPUs regardless of the vendor and the vector widths and everything else. And when it compiles for the most optimized version of that on your platform. We've still got a little bit of work to go there on enabling all the optimizations, and specifically with the Fujitsu compiler, we've still got some work, but that work is underway, and we can actually get most of the code that's written to Cocos today to compile on the platform. So this is very exciting for us. We think it justifies a lot of the work we've been putting in to the abstractions and making sure that they work everywhere that we take them. And then we've got Trilinus as well. We've got users out there that use Trilinus solvers for things, large scale applications, and we've got the initial builds of those running on A64FX. They're not fully optimized yet, but we do have that first enablement done, and we're just starting now on our open science application ports. Really, we've got to get the Cocos and Trilinus working before we can get those open science applications done, and I'm really pleased to show that we're able to get some of those up and running today, and we're beginning to start doing performance characterization and benchmarking of those codes. So that this is in the works, and we'll be happy to report on these in due course. But the early results for a lot of those solvers actually look great. We're really happy with that. So just a few things to think about if you happen to be at SC'20 or you're looking for some other talks from the group. We've got our an update on some of the lessons learned from Astra. It wasn't a completely perfectly smooth installation of a system. We learned a lot as we went along and brought the first petascale ARM system online on Wednesday the 18th. We'll give a summary of that in the SC architectures track. If you guys are registered for SC, please come join us. There's a lot of insight there into things that if you're deploying these kind of first of a kind systems that we think you need to worry about. And we'll talk a little bit about how we got around some of the problems that we encountered. So look forward to having you join us for that talk. Kevin and Andrew will be giving that talk, so they'll do a great job. And then if you want to know more about where we're at with our big Vanguard project, which brings in lots of ARM technologies, that's Astra and some of our testbeds and stuff, you can go to this site here, vanguard.sandia.gov. That's where we detail a lot of the work we're doing. There's lots of links and lots of resources there to a lot of our talks and presentations. So most of our resources are there, and you can use that as a launch pad to go find or download some of the software or the optimizations, etc. that we've been building for the ARM ecosystem. So before I finish, I just want to acknowledge, we bring these systems in. It takes a lot of people. We're really grateful for all the support from our colleagues across the labs at Los Alamos, at Lawrence, and our teams at Sandia. Specifically to Fujitsu and Penguin for enabling the early access, to the folks at ARM who help support us. The conversations around compiler optimizations and stuff have just been fantastic. Thank you for all that help. And then to the NNSA and ASC headquarters who provide all the support for our program, and encourage us to go out and collaborate with supercomputing centers across the world so that we can make the best of the resources we all have available to us. Thanks for all your help and support. We're really happy to acknowledge everybody's input for all the work that we do. So with that, I'll finish up. I think we'll probably have some form of ability to ask questions, and we look forward to hearing some of the queries and comments that you've got on our work. And if not, go to the resources and see what we're up to. And we look forward to hearing from you over email, etc. if you'd like to collaborate. For that, that's it for the talk, and keep safe and look after yourself.